coming to today's version of our inverse problems seminar series. So we are very happy today to have Leonid Kunyansky from University of Arizona, which is an expert in particular in hybrid imaging modalities, to talk about indeed hybrid imaging modalities and the range of spherical means transforms. Thanks so much for coming, Leonid.
Okay, I would like to thank the organizers for welcoming me here and for giving me opportunity to speak. That's one thing. And this is a very nice seminar, and I've been here once and I enjoyed it, and I'm going to enjoy it second time. And two, I would like to advertise a conference that many of you probably have heard about. That's IPMS, Inverse Problems Modeling and Simulation. It's a biennial conference that for the last several times we ran on Malta. So it's going to happen. The next one is in 2006. It's the end of May, I believe. You can figure out the dates. And it's a very nice conference with a lot of nice people. And it's a very nice place for a conference because it was beautiful and it's somewhat remote. That allows people to concentrate on mathematics when they are not enjoying the Mediterranean Sea and Mediterranean sun. So if you guys are interested, if anybody is interested, you can find it easily online, or you can ask me. I will gladly direct you wherever you need to go at that conference. All right, and I would like to apologize a little bit because this talk may be a little bit more on the introductory side of things. I didn't want too many technical details inside. The work that this talk is about has been just published at the Inverse Problems, the current issue probably. So you can easily find it if you're interested in any of this. And there you will be able to find all the proper references and all the technical details that I will necessarily skip because it's just a Zoom talk and not a paper. So this talk, the idea of this work started when we were visiting with Peter Kuchmet, my co-author and my former advisor. We were both visiting the Rich and Nonlinear Tomography program at the Newton Institute in Cambridge, where we spent some time together. And what happened is that Professor Venki Krishnan, that maybe many of you may know, actually he's from India, he came talking to us about certain symmetries that he and his collaborators, Guy Kambarsuman and some Indian, I guess, postdocs or graduate students, they found in the range of spherical means transform. So to give you an idea, so imagine that you have, I will explain all the details later, but imagine that you have a function that is sitting in a unit ball, and you compute all the spherical integrals with centers of spheres on the sphere, right? So then you have the range of your information really is from 0 to 2, right? Or all the spheres with the radius from 0 to 2 will intersect your original sphere and will give you some data. And what they found is that there is some symmetry between the data that you collected from 0 to 1 and from 1 to 2. And the symmetry is expressed through some differential operators that can be either very simple or more complicated, depending on which harmonics you're looking at. And we discussed this a little bit, and Peter said, listen, what it means, this symmetry would mean that essentially the range condition, so essentially that means that the first half of your transformation from 0 to 1 completely determines the second half from 1 to 2. And all the previous works on the range of spherical means transform, from this point of view, they are not optimal because they work from 0 to 2. The correct thing to do would be to analyze these transforms and from 0 to 1. And I said, yeah, and there is actually a tool to do that. It's not just an idea because prior to that, several years ago, we actually did work with Matthias Eller and my PhD student. Actually, the talk you can still find on this seminar website. It's still there, where we used a certain exterior problem to solve, to invert the spherical means transform and corresponding operators. And that allows you to essentially to do that. So we talked about it a little bit, and essentially this is how this work originated. All right. So what I'm gonna do, I'm gonna, again, with apologies, I'm gonna start slow and talk a little bit about regular Redon transform because I will need some of the properties. This first slide, of course, is very well familiar for all of you, right? In 2D, this is just Redon transform, just integration over lines. Lines are conveniently parameterized by omega and p, the normal vector and the distance from 0. You can do the same. Essentially, you can use the same equation gives you a plane in 3D or hyperplane in higher dimensions. So you would integrate over those planes or hyperplanes, and that would give you give you the Redon transform. And this can be used as a general definition, right? Because this is now in any dimensions, and we want to be general here. So this is integration. This gives you integration over a hyperplane. And what's important for my talk is that one thing that's almost immediately obvious, and most of you probably know that Redon transforms has certain symmetry. So this is the simplest symmetry, which is very easy to understand because it just, if you replace x by minus x and minus omega by minus omega, it obviously they also solve this equation and they define exactly the same plane. So if you go over all values of omega and p, you will count each plane twice. And this is where this condition comes from. There is a natural symmetry. I will give you in 2D, there is a simple illustration just to provide you some pretty pictures. So imagine this is 2D. This is some function that doesn't mean much, right? The yellow is positive, red is less positive, blue is negative. And so this is the Redon projection parameterized by the angle, which a normal vector does with, say, axis x. So the angle is here, and this is p. And you can see that there is definitely redundancy, right? Because this part of the image. Oh, by the way, can you see my cursor? Yeah, you get. Yeah, so this part of the image is the same as this, and this part of the image is the same as this, rotated and shifted, right? And so it's enough to know only half of that transform if you formulate it this way. Oops. Okay. But what's important? So one thing that I'm not going to mention, but it's important. I'm not going to give you any formulas, but it's important to mention is that Redon transform is easily invertible. There are, of course, very, very well-known inversion formulas in any dimensions, going back to Redon. And so we will use that. This is going to be important too. But the question that is more theoretical, and that was, of course, also answered by several people, I will give you a reference. Imagine that you now we take, for example, you can think of this as a cylinder, right? Because this is angular variable. This axis runs over circle in 2D, and this is kind of sort of vertical. In higher dimension, this is kind of generalized cylinder in the sense that omega is running on a sphere and p is running on the interval from -1 to 1. So you can think about this as a generalized cylinder. And so imagine that you are given a function f that's sitting on such a cylinder. And the question is, what is the condition for this function to be in the range of the Redon transform? In other words, what is the condition for this function so that we can find another function so that this function is the Redon transform of that one, right? And that the source function is supposed, of course, to be supported inside of the two-dimensional unit sphere. So this would be called, these conditions would be called the range conditions, and the necessary sufficient conditions have been found. So there are several authors. It was published not simultaneously in different times, in different countries, and in different journals by a group of Gelfand, by Helgason in his book, and by a guy named Ludwig, who was, I think, even a geophysicist rather than a mathematician. But nevertheless, they all found these conditions, and the conditions are as follows. So a function defined on, all right, so this should be S d minus 1, so defined on a cylinder, can be represented as a Redon transform of a function that's sitting in the unit ball, and this is a C infinity function, if and only if the following conditions are satisfied. So first of all, symmetry conditions. We already know that these conditions, we discussed this already, that these conditions are necessary. Well, but of course, so they need to be there. There is smoothness as support condition. It's very easy to see that if you have a function that is a smooth and is supported in a unit ball, then all the Redon projections also will be smooth in both coordinates, and they're supposed to be supported also in the cylinder, within the cylinder. And so these are kind of obvious, but much less obvious conditions are moment conditions. And I will try to explain them a little bit for people who maybe are not so much familiar with that. So in original works, like if you read Helgason, for example, it will say that moments that are defined by taking your candidate function and integrated it, and integrating it over, integrating it with the polynomial weights, monomial weights, this function should be a restriction of a homogeneous polynomial in omega of degree n. Now, this is kind of sort of not necessarily the best way of understanding it. So let's discuss it a little bit. So what that means, that if you take your moments and integrate them with spherical harmonics like so, then these moments should have zero oscillations for higher harmonics. So in other words, as a function of omega, these moments cannot oscillate too fast when you change omega. All right, let's put a little bit more discussion into that, because this is also not necessarily completely obvious. So let's look at the zero moment. What would be a zero moment? Imagine for simplicity even that you see it, for example, in two-dimensional situation. What's a zero moment? Zero moment means that first you compute projections, which is integration in one direction. Sorry, it's jumping again. And then you integrate it in P. Well, but then this is a Fubini theorem, right? It's a repeated integral, which means that this produces you an integral of your function, regardless of what projection you use, regardless of what omega you use, right? You just, each integral of each projection just gives you the integral of the whole function, which of course doesn't change. So this is a zero moment, and zero moment does not change at all. So it will give you zero if you integrate it with any spherical harmonics, except the zero one. Okay. Okay. Now, what would be the first moment? Let's now look at the first moment. Here's the first moment. First moment is the integral with the weight p. Well, if you remember your calculus 2 in University of Arizona, this would be. What that produces you, it produces you actually a projection of center of mass of your function onto your coordinate axis P. Well, if you rotate your coordinate system, you change your omega, right? So that projection also will be changing. So essentially this will be, if this is in 2D, this will be like cosine of alpha, where alpha is the angle between direction at the center of mass and direction toward your axis Right? So it will be changing. It will be changing as the harmonic with number 1. And if you integrate it with harmonic of order 2, it will give you 0, 2 or 3 or so on and so forth. So this is how it works. This is what these moment conditions really mean. They're not so difficult to prove as a necessary condition, but more complicated, more challenging, of course, task is to prove that these conditions, these 3 conditions that I mentioned, the symmetry, smoothness, and the moment condition, these 3 conditions actually also sufficient. So if you find a function on a cylinder, any function on the cylinder that satisfies these 3 conditions, you can find a lowercase f function that whose Redan transform corresponds to a function. Okay, so, and of course, this is all was very well studied. Well, it was studied even before the X-ray tomography was invented, and it was really studied in depth when X-ray tomography was a new thing, which was in the 60s. But kind of sort of X-ray tomography is somewhat old news these days. And the question is, are there any more exciting modalities? And the answer is yes. So again, with apologies to people who are experts in this field, I will give you just very short overview of hybrid modalities that are of main interest of mine. And so what is motivation? Motivation is the following, that X-ray tomography is far from perfect. So first of all, X-rays are very cancerogenic by themselves. So, and if in order to do X-ray tomography, you have to make many projections and expose your bodies or the body of the patient many times to strong X-rays. So by the time you checked for cancer, you may have given the patient a cancer, another one, right? Or a new one. So from that point of view, X-ray is not the best thing. And also X-rays, they essentially only show you one thing, the density of tissues. The attenuation of X-rays in the body mostly depend on the density of tissues. So it's very good when you need to image bones, for example. It gives a very high contrast. But if you like to look at the abnormalities in the soft tissues, they're not necessarily that informative. And of course, there have been many other modalities, and I don't want to even try to list them. But relatively new, the last 2 decades saw a proliferation of so-called hybrid modalities. And hybrid modalities are essentially trying to do the following. Sometimes they're called coupled physics modalities. And so the idea there is that you would like to couple 2 different radiations, 2 different sorts of waves. In many cases, one sort of wave is the ultrasound. Because ultrasound, usually when people work with ultrasound, they can go to pretty high frequencies and pretty small wavelengths, meaning that they can image very small details. It gives you a good resolution. But of course, the problem with ultrasound is by itself is that if you go with the tissues with strong changes of density, like bones, this is very nonlinear modality, which is very difficult to handle. And moreover, if you try to go to soft tissues, then the contrast is not so good, right? Like, for example, large motivation, strong motivation for this hybrid modalities was a search for a cancer, right? Cancer within soft tissues. But cancer itself is a soft tissue. So it's a soft tissue within soft tissue. The contrast with respect, for example, to speed of sound is not so large. So the idea then is to try to use 2 modalities. One would be ultrasound, but the other one would be, for example, some sort of electromagnetic fields, including optical or infrared waves, or just currents, electric currents, low frequency electric currents. Because all of these waves or currents, they strongly interact with cancerous tumors. For example, if this is optical modality, like thermoacoustic or photoacoustic tomography, it turns out that blood absorbs infrared waves much stronger than other tissues. And that means that you have very good contrast when you try to image blood vessels. So if you look actually at publications, practical publications, engineering and biomedical applications, thermoacoustic and photoacoustic tomography, you will see a lot of pictures of blood vessels because they provide a very high contrast. And it turns out that quite a few sorts of cancers, what they do when they grow, they like to grow fast, and for that they need blood. And because of that, they grow in a tissue a very large network of blood vessels. So if you look at the blood vessels picture, and if you see this big chunk of disordered blood vessels at some point, this is a good indication, for example, that this is cancer. And so this is why interest to all this alphabet soup of electroacoustic and magnetoacoustoelectric and acoustoelectric tomographies and so on and so forth. You can see that these are not the all modalities that have been proposed, because if you are good, if you have some expertise in combinatorics, you can combine randomly magnetic, acoustic, electric, photo, and thermal radiations and produce many different modalities like that. But I will mention just someone. So one of these, the most developed and the most practical one at the point, is thermal and photoacoustic tomography. And it works the following way. You surround the tissue of interest by detectors, meaning transducers really, or microphones or hydrophones. And you can put some gel on it, or you can put it in water, so to provide a good acoustic contact between the tissue and your microphones or hydrophones. And then you send in electromagnetic pulse, which is in reality can be either a pulse of infrared laser or microwave radiation, but very strong and very short. Right? It should be instantaneous from the point of view of the ultrasound propagation, which is possible because electromagnetic waves are much faster essentially than acoustic waves. And then what happens is that your tumors will absorb much more energy than all the other tissues. And when they absorb energy, they expand a little bit. And expanding, meaning that there is acoustic wave propagating outwards that will be captured eventually when it reaches the surface. It will be captured by the detectors. So usual picture is that you have this measurement surface that is covered by the transducers. In practice, they should be open. Mathematicians frequently consider for simplicity closed surfaces, but the main assumption here, the important assumption, is that we like to think that our detectors do not perturb the acoustic wave. So the acoustic wave propagation happens in the open space. There is no boundaries. And this is important because otherwise you need to solve a slightly different problem. Well, so what's the formulation of the problem? So I'm gonna look at the simplest one. So we assume that the constant speed of sound, and if speed of sound is constant, which is a good approximation for soft tissues, for example, then you can actually rescale your wave equation to make speed of sound be equal to 1. It's easy rescaling. So I will just assume that speed of sound is 1, density is 1. So my wave equation is really simple here. It's just this, right? Regular wave equation. The initial condition is the following. So for the pressure at the moment 0 is the function. It's the initial pressure. The derivative is equal to 0. So we're assuming that this initial pressure is deposited by electromagnetic radiation instantaneously, essentially. Right? And we assume that we surrounded the initial pressure is supported within a bounded region. The boundary is a closed surface, and we do the measurements on the surface. So for this talk, it will be the whole, not as a subset, but the whole surface. And then the inverse source problem is to reconstruct the initial source from the measurements that are done on a cylinder. Here is a picture. Right? So imagine that our domain is two-dimensional for this picture. The third axis is time. right? So that means that our function, our f of x, initial time is sitting here, this green lines. And then the boundary is here, but we measuring it all, we give it third dimension by measuring the time, measuring in the time. So the data that we measure in g of t is sitting on the surface of the cylinder. And if one wants to understand how the inverse problems can be solved, which is not the goal of this talk, but I have to mention it because this gives us some understanding. So usually people think about solving this wave equation backwards in time, because after certain time, which I denote t equals t capital, there will be zero pressure here. So if you are working in odd dimensions, like for example, if you're working in 3D, this is just a Huygens principle. After a certain time, there will be zero here. If you're working in 2D, for example, or if you want to be theoretical and work in other even dimensions, it's not going to be zero, but it's going to be small enough. When it gets small enough, you can just, ignore it, set it to zero, and solve back in time. Now you're solving the problem in the cylinder with initial condition zero here, both the derivative and value of the function, and the data, the boundary data given by your measurements. And when you get to the time t equals zero, you will reconstruct your function. So if you try this numerically, it doesn't matter really how you cut it. I know that people who look at this theoretically, they propose usually to cut it using the harmonic extension. So theoretically, this is an improvement because it improves the smoothness of the solution. From a practical point of view, I tried to do it. It doesn't do much improvement. So it doesn't matter. You can always assume this. If you are working in even dimensions, you can always assume that this t capital is infinity. And you can solve from infinity. And so this is how the inverse problem is supposed to work. It's a solution inside the cylinder backwards in time. But this is not the problem that we are looking at. And yeah, I would like, so before I go further, I would like to notice that what I formulated, the problem that I formulated before, is formulated in terms of the wave equation. But of course, people who started studying this, they started studying this like Peter Cushman and Agranovsky and Todd Quinta. They started studying long before the hybrid methods were invented and photoacoustic tomography became a thing. So they were looking at this problem from the point of view of spherical means, integrals of a function over spheres, normalized or not normalized. But there is a connection between this and that, because as you all well know, the solution of the wave equation can be expressed as an integration with the Green's function, with the fundamental solution, free space fundamental solution in this case. And for example, if you work in 3D, this is the Green's function, and then this will be nothing else as a scaled integration over spheres, right? So in other words, the solution of the wave equation can be expressed through spherical means, and spherical means then can be expressed through the solution of the wave equation. So these two problems, in a sense, can be reformulated as one through the other, and they're equivalent from that point of view. All right, just to give a little shout out to my own interest, I will not talk much about this, just another motivation. So I mentioned just one hybrid modality. But let's look at another one really quickly without much of the formulas. So what's magnetoacoustoelectric tomography? One of the modalities that I mentioned. You take a magnet, big magnet, you put your object of interest in a tank with saline solution, and you put acoustic transducer, you make it radiate some acoustic waves, and you measure the potential on the boundary of your tank. Now, these many electrodes are just my compliment to mathematicians because they like to think about boundary data. As a matter of fact, you just need 2 or 3 pairs of this. You don't need that many. But so how does it work? So when your acoustic wave propagates, it moves material particles back and forth. But in all the conductive tissues, there are ions and electrons that are free to move, right? And what happens when you move ions or electrons, charged particles in a magnetic field? Well, there is a Lorentz force, and the Lorentz force will move these particles aside, but the direction depends on the charge of the particle. That means that in this picture in particular, the negative ones will go this way and positive ones will go this way, thus creating electric potential. And electric potential immediately leads to ohmic currents that propagate through the whole object. And that means that there will be potential difference that you can measure on the boundary. You can measure it on the boundary of your object, right? And then your inverse problems is first to reconstruct some electrical processes in your inside of the object, and then try to reconstruct the conductivity, because again, conductivity is related to the density of the blood vessels, and the density of the blood vessels is the indication of the cancer. All right, so I'll show you just one formula, and I will go away. So you can show that in this situation, the measurements, the electric measurements can be expressed like this. What is what here? So I imagine that your impulse is generated by a point transducer and a delta function input, right? Then the function, what the acoustic pressure that propagates, this is just a Green's function of the wave equation. This is just a fundamental solution, right? Because this is what fundamental solution is, right? It's a response to a delta stimulation at one point, right? And the measurements will be just integral of this Green's function with, Green's function with the projection of curl of the curl of the currents dot magnetic induction. But my point here is that if you do a lot of these measurements, you end up at the same problem. If you think of this as a source that you need to image, then this is the same problem as before. You have a source convolved with the Green's function. So this is again the first step of this. This is again the inverse source problem, right? Of course, after you find the curl of your currents, there is electrical problem that you need to solve. But just believe me if I tell you that that problem is not that complicated, right? So the first step would be to find this, and this is again inverse source problems. So this is what motivates my interest to inverse source problem, acoustic inverse source problem. And so this situation arises not only in the modalities that I mentioned, but almost every hybrid modalities that use ultrasound essentially require you to solve as a first step acoustic inverse source problem. So there is some generality about what I'm doing. All right, let's go back to the forward problem. So inverse source problem, what is the forward problem? The forward problem is this. You already saw this, right? So this is a solution of the wave equation in the whole space, subject to the Cauchy conditions, right? F of x, for example, if it's a forward problem, f of x is given, right? And solution represents the excess pressure in the acoustic wave. We assume that the initial function is supported within the unit pole, and the measurements are the value of the pressure on the unit sphere times the time interval. So this is enough. With this data, we can define the observation operator, right? So this is an operator that maps our initial condition into the data that we have on the cylinder. And so, as I said, the case when you measure the stuff for times greater than 2, which is the time that all singularities propagate out of the ball. This case has been studied before. I will mention some important results there. But our main interest is when the time interval is from 0 to 1. Again, as I mentioned, and I probably should skip this a little bit, this problem can be reformulated as integral of the spherical means, right? And then we can pose a corresponding problem for the spherical means operator. So you would consider the operator that takes the initial condition and maps it into the values of spherical means collected on the band with the centers on the sphere, right? And we want only to look at the radii from 0 to, well, r, which is 1 in our case. So this should be 1. This is what we're interested in this talk. So here are the 4 problems of interest, right? So you can consider either inverse problem for wave operator, you can consider inverse problem for spherical means, or you can try to look at the range conditions. This is a different problem, right? So we would like, out of all these 4 problems, we would like to concentrate at the moment on this problem, the range conditions, third problem, range conditions of the wave operator, while keeping in our minds that this is essentially equivalent to the problem about range condition of the spherical means. Why I'm mentioning this is because some of the most important works here were done in terms of spherical means, right? But they're equivalent in a sense. They can be reformulated for the wave operator. All right. So how would range conditions look in general? So in the beginning of the talk, I mentioned some range conditions on the Redan transform, the regular Redan transform. So Agranovsky, Kuchman, and Quinta, for example, found this range condition for spherical means. Here is the condition. You have to take your spherical means and integrate them with the normal derivative of some eigenvalues, eigenfunctions of the Laplace operator in the sphere, with the ways that are some sort of Bessel functions, and so this integral should produce U0. This is how the range condition would look like. For example, they've been later reformulated in terms of momentum conditions. This is also possible. But I just want to tell you that, first of all, this is the paper that I'm quoting is 43 pages of rather heavy mathematical analysis. And the reason is that while the necessity of these conditions actually not so difficult to verify, proving that these conditions are sufficient is quite a challenge, right? And so there was second paper where this first paper was finished. So this is a lot of pages of heavy mathematics. But notice that we are not going to look at this much because you notice that integration here is from 0 to 2, right? So they're using all the radii. We only want to use radii or times from 0 to 1. So this is what's new in this talk, right? So we are going to work with function b given on the interval, time interval from 0 to 1, or this can be reformulated for spherical averages given an interval from 0 to 1. All right, how are we going to do this? So the tool that can be used here that makes this problem actually relatively simply solvable is the following. We want to look again, we want to go back to the Redan transform. And we want to look at the Redan transform of the solution to our Cauchy problem, right? And so we can, this is the Fourier transform, sorry, the Redan transform of the initial condition. And this is, and this is the Redan transform of the solution. And then there is a very simple theorem, well, very important theorem that's actually relatively simple to prove, is that if you compute the Redan transform of the wave equation, and if you fix omega, the direction, and look at just one projection, this one projection is a function of t and p, right? This is what it's function of. Omega is fixed. Well, it turns out that as a function of t and p, the projection satisfies the one-dimensional wave equation. Well, but for one-dimensional wave equation, this is PDE's 101, right? So this is the solution. This is D'Alembert's formula that everybody knows, right? And it shows you that there will be two waves, two halves. One half of the initial condition propagates to the right, and one propagates to the left, right? Which means that, for example, if I know the solution, the Fourier the Redan transform Y solution at the time 1, it gives me 1/2 of projection, and the other one gives me another 1/2, right? And so I can reconstruct, I will have two copies, and I can reconstruct my initial condition just by inverting the Redan transform of it. because the Redon transform of my initial condition is expressed to Redon transform of my wave equation. Okay, what does this have to do with problem in mind? So what I want to do, important tool will be this. I want to consider not the problem inside the cylinder, like everybody else does going backwards, but I want to solve the problem for the wave equation going forward and outside of my cylinder, right? So this blue picture in blue gives you the domain where my solution will live. It lives outside of the sphere, right? And this red picture shows you where my solution is supported. Because, what solution? So at the conditions at time 0 are 0, right? In the plane. But I'm imposing the boundary condition. So I'm taking my candidate function that I'm trying to understand on the cylinder, and I'm using it as a boundary condition for my wave equation. And because of that, because the speed of sound is 1, my solution will be supported within this reddish cone. Now, how am I going to do this? What it's for? Notice that if my solution of the exterior problem, which is called V, has the same, if I'm imposing the same boundary conditions as the trace of U of the solution of the Cauchy problem on my cylinder, then outside of this cylinder, these two functions will coincide. These two solutions coincide. Well, because they're both solutions of the wave equation, that they have the same boundary conditions outside. But then what I can do, I can take the Redon transform of my exterior problem, and if I can compute the Redon transform, and if U coincides with V, the Redon transform of my exterior problem will give me just the Redon transform of my initial condition, right? And what's good about this is that I only need to solve from 0 to 1. I don't need to go from 0 to 2, right? Because I only need to get 1/2 of my projection on the right, and the opposite projection in the opposite direction will give me the another half, right? And so by doing this, if I'm using the correct function, if my function V coincides with U on the boundary, I will be able to reconstruct F. Here is a picture. I want to give you a picture on how this works. So this is an illustration. This is my initial condition. This is my unit sphere, unit circle. This is my initial condition. This is a solution to Cauchy problem. In this picture, it was solved till time equal 2. This is a solution with exterior problem, with the conditions on the boundary given by the trace of this solution. You can notice that outside of this circle, these two functions, at least visually, coincide. Inside, this is exterior solution. It doesn't exist inside here, right? How can I use this? Here is another illustration. So I'm going to take this solution in time 2, for example, if I want to compute the time 2, and compute Redon transform, exterior Redon transform. I cannot compute inside, because inside the function is not defined inside the circle. But I can compute this Redon transform, right? And that Redon transform, now if I take these 2 halves, if I compute it only to time equal 1, I take 1/2 from here and 1/2 from here, glue them together, and this is my candidate function. This is my candidate function for the source, right? So what good this gives me? That gives me, because this is a candidate function for the regular Redon transform, I can apply to this regular Ludwig-Helgason-Gelfand conditions for the regular Redon transform. And the good thing is that these conditions are not only necessary, but they're also sufficient, right? And so what are these conditions? That means that on F, the following condition should be satisfied. This is just Gelfand's condition. So first of all, my function, my candidate function B should be smooth, right? Because otherwise, the projection will not be smooth, and they must be smooth for this to be a Redon transform of a smooth function. Second, the smoothness of my candidate f here, the Redan transform, it should be on the whole interval from -1 and 1. So this imposes additional condition because notice I'm gluing my candidate projections from two halves, right? That means that if I want this to be a Redan projection of a smooth function, they should glue smoothly at 0, right? And then third, the moment condition. The moment condition need to be satisfied. And so these are the initial, sorry, these are sufficient and necessary conditions, right? And these are the conditions, essentially, these are conditions on B. How are these conditions on B? Because this is directly on B, but function f is defined by solving the exterior problem where B is a boundary condition. So these conditions that I have here on these slides, they are somewhat implicit because they are formulated in terms of exterior problem, solution of exterior problem. Okay, I see that I'm running out of time a little bit. So I will try to give you, so there is a second step. There is a second step on this. So second step is the following. Let me go just a little bit. Right. So this is what I want. This is what I would like to discuss. So this is a condition. This is just the beginning. This is just the main tool that I'm using. This is this sufficient and necessary conditions that I have formulated. They are formulated in terms of the solution of the exterior problem. Now, to be good mathematicians, we want to formulate these conditions in terms of the function B itself. And this is what we do. We take Fourier coefficients of our candidate function B. We expand it in spherical harmonics, right? And then what we do, we find with the details in the paper, we can solve because our geometry is spherical. We can use the separation of variables and solve the exterior problem in terms of spherical harmonics, and also expand the Redan transform that we are trying to understand in spherical harmonics. So the Redan transform that we are trying to understand can be expanded in spherical harmonic with certain coefficients, and these coefficients are found by doing this stuff, by doing the separation of variables, as a convolution of the coefficients of the original function with certain kernels. And these convolution kernels are given by some ugly inverse Fourier transform of something. So these kernels are the distributions. Question is, of course, whether these kernels can be expressed in a nicer form. And so the answer is maybe. I'm not sure. We have not done that. There may be some way of expanding this as some, I don't know, some ultraspherical polynomials or maybe some other solutions of hypergeometric equations or something like that, hypergeometric functions. I don't know. But what is known that these are just distribution, and what's important is that this formula here is a convolution. And it should be a convolution, right? Because the problem that we are solving in the time direction is invariant to shift, right? Because nothing depends on time, so the problem is invariant to shift in time. And that means that the solution of this problem with respect to time should be a convolution. And it is a convolution. Moreover, this is something that I called crudely, I called it as a Volterra convolution. So notice that the integration here is from 0 to the certain upper limit. Now 0 is simple. 0 is just because our function in time is defined from 0 going up only, and we extend it by 0 going to minus infinity. But the upper limit is not infinity. The upper limit is t plus something, right? So this is sort of a convolution that arises, for example, when you work with Laplace transform, right? One-sided convolution. And this is good. Why is this good? Because that means that we see here the causality of the solution of the wave equation. So the solution that our Redon transform depends only on values of function b that were prior to the time t and not after that. We are not using the future values. And this is important both from philosophical reasons and also from reasons of our technique, because these solutions that we found, it was formulated going to Helmholtz equations, which means that it was formulated by using the Fourier transforming our solution in time. And in order to properly Fourier transform it in time, you have to define it from minus infinity to plus infinity in time, which means that we had to extend our measurements from time t equal 1 to c infinity going to larger values of time. This sort of extension is arbitrary. It's possible, it's always possible. It's so-called Borel lemma, which I've learned recently from Peter Cushman, right? But such extension is arbitrary. However, because our kernels are given by convolution kernels, they vanish for t less than -1 in the sense of distribution. When you look carefully at how the solution is written, you see that nowhere here we are using the values of the coefficients for time greater than 1. So meaning that although we use the arbitrary smooth extension to times greater than 1, we explicitly not using those values anywhere. So our solution is well defined. Okay, I stole 3 minutes from you. I apologize. Yeah, so this is the main result, which is essentially tells us that these coefficients that we found should satisfy the moment conditions, and they satisfy the certain smoothness conditions at 0, because we are doing the gluing of two parts of the Redon transform into one. There should be some derivative should be vanished here at 0. I don't have time to go into detail, so I will just stop here and I will accept your question.
Okay, thanks so much, Leonid, for a very nice talk about and very interesting contexts. So indeed, the floor is open for questions. If anyone has questions, please unmute yourself and ask questions. So I was wondering, Leonid, so from the point of view of the application, you may have some noise in the data. So how would you say about the robustness with respect to noise when you use this spherical means approach there compared to back projection or in the imaging?
Yeah, I understand it. So first of all, there are some about robustness of this. So first of all, if you analyze the problem itself, the inverse source problem for the wave equation, you will see that actually, strangely enough, it's actually well posed, right? Second, the back projection and the filtered back projections formulas that were derived for this, they actually can be proven. I actually have done that. This can be, for sphere at least, that can be done using, again, the spherical expansions. So they're essentially equivalent, right? So it does not produce any complications at all. This problem, if you look at some experimentation, you can give it noise at 20 and 30%, and you get a pretty decent reconstruction. Exactly not because the algorithms are so good, but because the problem is good, right? If you try to go through the Redon transform, in practical sense of view, it still works very well because your data is still good. When you try to do the Redon transform directly, you actually smooth out any noise that is there. And of course, you pay for that You pay for that because the inversion of the Redan transform, especially in the higher dimensions, the higher the dimensions, the more ill-posed it become. Right? If you look at the Sobolev space estimate in 2D, the difference between the original space and projections is 1/2. If you look at 3D, the difference will be 1. If you look at 4D, the difference will be 1.5, and so on and so forth. So if you go to Redan transform, you actually increase the ill-posedness, but you compensate for that because when you compute yourself the Redan transform, you actually smooth things out. And if you look what we did with when we essentially the second part of the talk that I mangled, about going to spherical means, it essentially bypasses the direct computation, goes directly from B to the coefficients. And it's just reasonably well posed, because if you look at those integrals, there is, the Bessel functions do not decrease that fast at infinity. You don't lose much. So in practical terms, it works actually very well. And you can do things that you cannot do any other way. Like, for example, reconstruction from half time. This is something that practitioners are like very much, because it makes the measurement cheaper, right? And another thing is that this model of the wave equation, it's an approximation, right? The speed of sound is not exactly constant, and there is attenuation, and there is dispersion, and there is this, and there's that. So the longer you measure, the more error you accumulate. So from that point of view, if you reconstruct from 0 to 1, you use good data. If you try to use the data from 1 to 2, this is already worse. And so this approach allows you essentially to do that naturally. You don't have to do anything else. So from that point of view, this is a good thing to do. Now, I don't know how much. It's a question. It's a debatable question of how much these range conditions would help by themselves in terms of applications. I think that at some point, Sarah Patch, with her collaborators, was trying to use range conditions to improve the data, the experimental data. From what I remember, the results were rather moderately successful. So other people have not continued doing this. Right? So that part I don't know. But as a theoretical result, I think it's pretty important.
Great. Any other last questions for Leonid? Well, otherwise, thanks again so much, Leonid. Very nice presentation.
Thank you.